Okay, let's just dive right into this explainer with a massive, kind of mind-bending question. What if we could perfectly predict exactly how a complex new material, or, even an entire machine is going to behave without ever actually building the thing? Well, welcome to the atoms to engines revolution. We're looking at an absolutely fundamental transformation in how we design, test, and just basically understand the physical world around us. Historically, engineering and design relied heavily on physical trial and error. I mean, you know the drill. You build a prototype, you test it, it inevitably breaks, you spend a total fortune, and then you just start all over again. But today, we're molding our physical world using what I like to call digital clay. These are virtual simulations that are infinitely malleable, totally safe to break, and incredibly cheap to reshape. We're literally swapping out heavy steel and physical labs for algorithms and high-performance computing. It's wild. So, to understand how we're actually pulling this off, here is our quick roadmap for today. We'll be covering Welcome to the Virtual World, the end of physical prototypes, accelerating new material design, powering tomorrow's energy tech, the AI and supercomputing synergy, and finally, validating our virtual future. All right, jumping right into sections 1 and 2, the end of physical prototypes. Let's look at our first core concept and see how entire industries are just completely ditching physical builds to save massive amounts of time and money. I think this crucial point is captured perfectly in Formula One racing. Right, so teams used to spend millions manufacturing physical wings, bolting them onto a car, and running them on a physical track. Today, that whole process is completely flipped. Thanks to advanced aerodynamics modeling, a staggering 90% of prototype parts are tested entirely in high-fidelity virtual simulators. Basically, 9 times out of 10, only the components that actually prove their worth virtually ever see the light of day. It is a stunning gain in efficiency. And this brings us to the whole concept of the digital twin. Now, this isn't just for racing. The automotive, healthcare, and manufacturing industries are all creating these comprehensive, all-encompassing virtual models of their physical systems. Imagine being able to test emergency room safety protocols, or predict exactly when a massive factory machine is going to fail, or optimize vehicle aerodynamics, all safely and entirely virtually. Why does this matter to us? Because it means safer cars, more efficient hospitals, and way better products hitting the market way faster. Moving right along to section 3, accelerating new material design. Now, to really appreciate this digital clay concept, we have to zoom way, way in, down to the absolute smallest scale, the atomic level. Taking a look at this space-time scale chart, we can map out physical-chemical phenomena and the actual computational methods used to study them. We call this multi-scale modeling, and it shows how we use all these different methods, starting all the way down at quantum mechanics for electrons, moving up through molecular dynamics, and eventually hitting continuum electrodynamics. We're doing all of this to understand exactly how systems are going to behave before they even exist in reality. But here's the catch. Doing absolute first-principle quantum calculations takes an immense amount of time. So to bypass this massive computational bottleneck, researchers are now industrializing machine learning interatomic potentials, or MLIPs for short. A really great example from our sources is Matlantis's PFP model. These pre-trained AI models give us density functional theory level accuracy, which is a fancy way of saying quantum level precision, but at the blistering speed of classical computing. It's almost magical. Engineers can now sculpt and predict how completely new materials will react without waiting weeks for the math to finish. And this brilliantly illustrates the kind of precision we're talking about here. Instead of calculating a material's properties only at absolute zero, which, let's be honest, isn't very helpful for the real world, we can now model dynamic, real-world temperature behaviors. We can literally watch hydrogen diffuse or oxides migrate at the molecular level in conditions that perfectly mirror the exact harsh environments these materials are going to face out in the field. And you know what? The barrier to entry is dropping fast too. Platforms like CameraFine are utilizing natural language AI to completely automate this whole process. A researcher can literally just type out a plain English description of the molecular workflow they want to run. The AI then grabs that idea and translates it into a fully simulated click reaction or drug transport mechanism, handling all that wildly complex quantum integration automatically in the background. It's a total game changer. Okay, section 4, powering tomorrow's energy tech. So we've seen the atoms, but now let's scale things up to the engines. Let's see how this digital clay accelerates the design of massive macro energy technologies. Over at the National Renewable Energy Laboratory, Their Kestrel supercomputer, which is running at a staggering 56 peak petaflops, by the way, is managing hundreds of virtual projects. For instance, the ElectroCat team is busy screening cost-effective, critical mineral-free battery materials. And the bioreactor design tool, it's letting researchers test and optimize complex gas-liquid flows in industrial bioreactors, completely virtually, long before a single piece of physical steel is ever caught. We're also using computational fluid dynamics, or CFD, for some massive environmental challenges. Just take a look at this modeling. It simulates the highly complex interactions of extreme ocean waves crashing against offshore wind turbine foundations. By doing this virtually, engineers can accurately predict long-term erosion and structural fatigue in incredibly harsh environments without having to literally wait decades for the real-world wear and tear to show up. Let's zoom out even more to our cities and see how this builds into even larger human ecosystems. Scaling up further, this simulation reveals the cascading effects of infrastructure failure. Right here, we can see how a localized power cut doesn't just stop the lights from working, it completely disrupts the mobile telecommunications network in real time. And this is exactly what happens when we start stacking these digital infrastructure layers: traffic, public transport, power, gas, internet. By combining them all, we create this massive system of systems. Planners can run scenarios to optimize pedestrian evacuation routes during an emergency, or they can test exactly how adding a new power grid is going to impact everyday traffic flows. It's an entire living city made completely of digital clay. Section 5. The AI and supercomputing synergy. Now, obviously, none of this, not the atomistic predictions nor the massive city-scale simulations, would be possible without a massive, foundational leap in the actual hardware running all this math. We are officially entering the exascale era. High-performance computing is rapidly moving away from your traditional monolithic supercomputers. Instead, we're seeing these fully integrated digital continuums. By blending cloud resources with artificial intelligence and shifting workloads onto massive GPU-based accelerators, industries are just drastically cutting runtimes. In structural engineering, for example, complex scenario testing that used to take like 1,000 hours, it's been reduced to just a few hours. And this synergy ultimately creates the atoms to engines workflow we've been tracking today. Because computation is just so incredibly fast now, high-speed data generated at the molecular level, say, the behavior of a specific alloy's atoms, can now be instantly embedded directly into larger-scale continuum models. You can evaluate the fracture toughness of a massive jet engine component in extreme conditions by literally looking at how its individual atoms are behaving in the simulation. Mind-blowing, right? All right, final part, Section 6, validating our virtual future. Now, all of this sounds absolutely incredible, but it does raise a really important question. How do we actually know our digital clay behaves like the real world? Like, we aren't just creating very expensive video games here, right? Because models are, by definition, always simplifications of reality, they have to undergo extremely rigorous verification and validation. Verification basically ensures the math and the code are built correctly to match the conceptual model, fixing any errors along the way. Validation then checks if that model actually represents the real-world system accurately. Organizations like the American Society of Mechanical Engineers, or ASME, have established strict credibility guidelines to ensure these simulations aren't deceiving decision makers. Basically, the digital twin always has to be held strictly accountable to real-world physics. As this technology evolves, bringing in quantum computing and even deeper AI integration, the line between physical testing and virtual simulation is really going to continue to blur. Think about that for a second. If our digital clay becomes so absolutely perfect that we can flawlessly predict the behavior of a new material, a jet engine, or an entire city grid before it physically exists, what parts of our physical reality will still need to be built just to be believed? It's a fascinating future, and one we are already building, virtually. Thanks so much for joining me on this explainer, and I'll catch you in the next one.